My goal for today is to get through the rest of the tutorial that I started last week, and then we'll hopefully be able to get out here a little early today. My understanding is that everyone's got a partner now, I think. Were there any issues in lab this last? What failed?
The board, so it failed.
And
You used the USB port. You wanted to,
They won't flash it.
yeah, so you want to flash it, it would fail.
yeah, I heard about that. I think what happened was last year, Viraj went to surplus and got a bunch of cables, and I think some of them were bad. So if you have any trouble flashing, then try a new cable, USB cable. I apologize for that. Any other issues? Okay. Okay, good. So last time we got a project up and running in Quartus. So I've got Quartus open here, and I have the top level Verilog file. It's called lights, and that corresponds to the top level name that's set under assignments settings under top level entity lights. Y'all see that? Make sense? So if you go to compile and it says you don't have a top level entity defined, that's where you would fix that. You just have to make sure that the top level entity is set up in the settings, and then there's a corresponding Verilog file and module with that name. It doesn't have to be called lights. It could be whatever you want.
Extension would be .v, right?
That's right. The top level module has a bunch of inputs and outputs. Most of them are for the DRAM in this case. So the DRAM has a fairly complex connection. Has an address, lines and data lines, and a whole bunch of control signals. Bank address, clock enable, row axis strobe, column axis strobe. These are all the wires that go from your processor to your RAM in any computer. All right, if any of you have upgraded your RAM, you pull out one of those DIMM modules. All of those conductors on the DIMM module are actually these signals. These are standard DRAM signals. We also have an input for the keys. There's 4 bits for the keys, and there's the clock that comes from the crystal. So all of these inputs and outputs match up to physical pins and wires coming off the FPGA. They have to, because it's the top level design. And if you're curious how that works, those names are set up in the pin planner. And so each one of those names has a corresponding location. And you can, if you click on them down here, you can actually see where the pin is. What you're seeing here is a picture of the underside of the FPGA. So all of this is a ball grid array, meaning that there's a 2D array of solder pads underneath the chip, right? And so, and you might be saying, wait a second, I thought chips had like pins around the edges, right? They do on some small chips, like on an Arduino, right? But on a complex chip like an FPGA, you want to have more pins that are available just on the periphery of the chip. So you go underneath the chip and you take advantage of that whole area underneath the chip to try to get as many pins as you can. There's 800 pins on this thing, right? And why is there so many? Because we want, the FPGA vendors want to provide as many pins as they can so you can use them for whatever you want to. You might say, well, how do I use them for stuff? Well, you can't, because by user, I mean whoever's making the PCB. So in other words, in order to connect one of these pins to something physical, you would have to do that when you manufactured the printed circuit board that you put the FPGA on, right? This company that we bought these from already made it, and so there are predefined connections between the pins and specific components on the board which are defined in the pin mapping file. Once you import that pin mapping file, you should see the pin mappings in the pin planner, right? So the first thing you should check if you download your design to the FPGA and it either just dies and doesn't do anything, or a lot of times what you'll see is it'll glitch out. It'll start to like have a seizure. You'll see lights just kind of flickering sort of randomly. If you see that happen, that means that you didn't import your pin planner. Your pin assignments file. You guys with me? Make sense? But generally speaking, if things don't work, that's the first thing you ought to check. Make sure your pins are mapped. Okay, so inside the top level module, I don't have much of anything. It's just, all it does is instantiate the system that was generated by Platform Designer, and then it just makes connections between the top level inputs and outputs and the connections on the system that you generated. So this is a wrapper. A wrapper is a design that does nothing but connect things coming in to something inside, right? You guys with me? Okay, any questions about that? Okay, so then inside the Platform Designer, we have the design of the Neo system. And this is the first semester we've used this tool. In the past, we used to use a similar tool called SOPC Builder, but it was actually easier to use. This one, I'm still getting used to this myself. The reason is that these connections, all the connections are made in this column labeled connections, and the clock and the reset connections are the ones that are really kind of tricky to get them all set up. Every time you add, generally speaking, every time you add a new component in here, you have to connect a clock and a reset. And then you have to make things even more complicated, you have multiple clocks for different, in this case we'll have three actually. There's a reference clock that comes from the crystal. I mentioned that we don't want to use that one on any of our components in there because it's got a lot of jitter in it. It's not a consistent clock signal, right? Its frequency varies over time. So we take that incoming clock, which is right here. This is the clock in, and it's exported, meaning that it's exposed as a top-level pin called clock. Now the one thing that is a little confusing is that notice I called the export clock, but if I go back to Quartus, it's called clock_clock. Why? I don't know. I have no idea where clock_clock comes from. But the suffix the clock that forms the suffix is, I think, what I typed here, CLK. You guys with me? So this could be, what I'm trying to say is that sometimes it may not be totally obvious what the correspondence is between exported signals in Platform Designer and then the stuff that's on the top level module that you have to connect in your wrapper. You kind of have to figure it out. You guys with me on that? Okay? All right, so clock comes in, and then I've got a reset comes in. Now, I've got the signal, the exported signal here is called reset. If I go back to here, it's called reset N. Yeah, reset N. Again, I'm not entirely sure how those names are generated, but it's not too hard to figure out. But notice that the pin on the Neo system is called reset N, but I'm connecting it to something called key 0. So I'm connecting the right key, which is active low, to the reset N. So this button on here is going to just go straight to the reset. You could tell that that's apparently a convention, because in this sample demo design that comes up automatically, if I hit that button, it sort of freezes. So it looks like Altera or Intel is using that same button as their reset as well, just based on the behavior when I push it, right? Okay, and then the DRAM stuff is, kind of complicated. Unfortunately, it's outside the scope of the class, so you'll just have to make those connections as I did. I think somebody mentioned, by the way, one of the TAs mentioned that there was a little confusion in lab because the SDRAM controller has an export called SDRAM, and this one export in here gets broken out into all of these exports. You guys with me? So having one export in Platform Designer may actually expand to multiple signals, multiple ports. And I think one of the TAs told me that there was a little bit of confusion about that. It wasn't clear in the lecture slides that that was exported, or I might have used a different name there, so I just wanted to point that out. Yes?
I was actually confused by something else too.
Okay.
The system clock is clock 1. I'm trying to connect, I was following the PowerPoint, we were following the PowerPoint. It was kind of confusing and then we got off of that, so that might also be something else because it didn't work when I connected it to the system clock. I didn't notice like the difference between clock 0 and 1. Because when you're trying to right click on it and try to connect it using the bar that it gives you, it actually is, it's really confusing. It doesn't really tell you 0 and 1.
Well, the clock 0 is when you see clock 0, that's the reference clock. That's the one you're not supposed to use for anything but feed into a PLL for a reference, right? Then the PLL is called CSCE PLL 0. I should have renamed that. You can rename that, I think, right? I think. Right click, rename somewhere. Yeah, okay. I should rename that. I'm afraid if I do it, is it going to break some? What the hell? Clocks. Clock. Just how about PLL? There we go.
Field, so if you
Okay.
right click on anything, you try to, there is a connect field, like a connect option. If you right click on that, there's a connect option. That's where the confusion happens because it doesn't really present the entire name. It only presents part of it.
Right, you talking about this one? This pull down menu?
If you go to the list where the name is, just right click on anything. You can from there.
Oh, here?
Connect or add.
Oh, connections. Yeah. Okay.
Connections don't really appear, especially if you have the window minimized.
Sure.
It's not really.
Sure, yeah, that's right. There's a couple ways to go about it. So, yeah, if you right click it, you can connect it. I have some options. Clock 0, that's my dirty clock. I don't want to use that. Clock 1 is exported, so I actually can't use that. I think you can use that, but then it'll unexport it, in which case the DRAM will lose its clock. PLL SDRAM clock and PLL sys clock. Now, just be aware that in the next lab we're going to add a VGA clock to this list too. So this is important that you can manage these clocks. Okay, so what he was saying was that you can do a right click and you can make connections through this menu. You can also, under the clock column, you can choose things there, or you can just click the little bubble over here on these wires. For the clocks, I think it's probably easier just to use this pull down list, right? Okay, so the bottom line is that everything in here should use the sys clock, except for the PLL, which has that clock 0, and the DRAM controller, which uses the DRAM clock. Okay? This is important because if you make a mistake here, this is one of those things that will cause it not to work, but it'll be a hardware bug, not a software bug, so it'll be hard to debug this stuff. Okay? So just be careful with this stuff. Okay, so the Neos has a sys clock. Also, I can click, let's see, if I click this clock, it connects to the PLL, so you can see how it highlights that path. The PLL has a sys clock. I can click that, I can see that going into the processor. And, well, that's it for now, because I haven't added the rest of the stuff. There's also an SDRAM clock that goes to the DRAM controller, and it also goes to this clock in, so I can export it. Everyone with me? Okay. All right, so that's the whole design. So what's the next step? We need to add some I/O devices, some more I/O devices, because currently all we can do is we can configure the FPGA, we can download the ELF file, the program code, but the only way for us to interact with it is through the debugger. which is common. Your phones will do this too. If you have an Android phone, you plug it into your laptop and you download ADB, the Android debugger, and it creates a similar type of debugging interface, which is great if you're debugging, but if you want it to actually do something functional as a product, then you need to add some other I/O peripherals. So let's see. The first one we want to add is a console. I think that's the right order. Let me double check here. Yeah, Jtag Uart. So a Uart is kind of an old word, but people still use it. A Uart is just a way to do a text-based console. Uart stands for Universal Asynchronous Receiver Transmitter, but it's really just it's people nowadays they have it go over USB. Back in the old days, they used serial ports. And in our case, it not only goes over USB, but it actually gets carried by Jtag. Sorry, does it? It gets carried over the USB blaster, which is USB, right? So we have this one cable where we can program the FPGA and get the console. You guys with me? Make sense? So we can print messages. We can also type stuff in as well, although generally we don't do that in this class, but you have the option of doing that. All right, so how do we do that? Type Uart and just add it, Jtag Uart right here. These options you can leave as default, so just click finish so it adds it. Now we have to connect the clock, so I'm going to say PLL. Notice I just changed the name of that. See how it says PLL now? Phase lock loop. I just changed the name of that thing. So it says PLL sys clock. Yours may be different, but just look for the sys clock at the end. So I'm going to clock this on the sys clock. And the reset, I'm going to use this clock reset right there. I'm going to make that connection. See how I did that? I clicked the bubble. Why? What is that? That's the button. That's going to become directly from the button on the board. And you hit that button, it's going to reset this Jtag Uart as well. Why do we have to reset it? You probably don't need to, because it'll get initialized from the processor. There's a control register on there that the processor uses to set it up. So if you forget to connect the reset, it probably will still work. But it's good design practice to have everything on one. It's good design practice to have a hardwired reset into everything. Jtag slave. Be very careful here. We want to connect the slave input to the data master, not the instruction master. This is a very common problem that people make. If you connect it to the instruction master, then from the point of view of the Neos processor, it's going to think that the Jtag is a source of code, as a source of instructions, right? Which obviously it isn't. It's meant to be a peripheral. And so you want to be able to access it through the load and store instructions, right? Not through the instruction interface, right? So if you connect the instruction master but not the data master, then it won't work. Your CPU will print and just nothing will come out. And again, you'll be, your first instinct is look for the software, but it won't be a software problem, it'll be a hardware problem. This is a very easy mistake to make though. Look at how close these bubbles are. Although, as Ibrahim said, you could probably just right click it and say, yeah, so you can right click it. I think this is a better way to go. I think you're right. If you right click it and go to connections, I can just connect as data master right there. There we go. And it makes the connection without having to hunt for the little tiny bubbles in there. The IRQ, there's only one IRQ receiver, and that's on the IRQ of the Neos. If you don't connect that, I think it will still work, because I don't think it's necessary unless you're doing input. Like if you, that's for example, if you want to write code to say press any key to continue, then I think the interrupt would be used in that case. But again, you should connect it back to the processor anyway. Everyone with me? All right, that's done. Next, parallel I/O for the LEDs. So there's 18 red LEDs, there's 8 green LEDs. We want to treat them all as one bus of LEDs, one register of 26 LEDs, right? You don't have to, but in this, I want to have the code kind of just use them all as one big output device. So we're going to add a PIO, parallel I/O, which is just, for those of you that are into Arduinos, this is just a GPIO, general purpose I/O. It allows you to do what some people call bit banging, which is where you can set individual bits from the software, right? Without going through like a driver, right? So, double click that. And width 8, well, we certainly don't want 8. We could just use 32, which is the native width, but I'm going to say 26, and I'm going to make it an output, and the reset value is 0. And just leave everything else the same. 26, I'm going to rename this too as LEDs. And now I have to go through clock, right click. I'm going to connect the clock to sysclock. I'm going to connect the reset to the clock 0 reset thing. The slave will be connected to the master, data master, and the external connection I'm going to export as LEDs. Why do I have to export that? Because this is something that I have to bring outside of the system so I can get to the pins. Okay, that's it for that. And then next, I want to do another parallel I/O for the keys. So I'm using key 0 is the reset, but I want to be able to use the other 3 keys for input, right? Because the LEDs will be an output, and I'll use the keys for input. So I'm going to add another PIO. I'm going to say 4 bits. 3 or 4? Should I do? What did I use in the tutorial? 3 bits. Sorry, we'll do 3 bits. These will be input, and hit finish. And then I'm going to rename this to be keys, and then just hook up everything else the same. So connections, let's see, keys will have a sys clock. The reset will be clock 0 reset. The slave will be on the data master, and the external connection will be exported to keys. All right. So I've got some red error messages saying that there's some address overlaps. I don't know why the tool just doesn't automatically select a non-overlapping addresses. What this is referring to, by the way, I don't know how well you can see that from the back, but if you look at the base address column, notice how the keys start at address 0. But so do this, the LEDs start at 0, and the Jtag Uart starts at 0. So these are all clashing. These are all conflicting with one another. You don't want these addresses to overlap. You want them to have their own unique, distinct address ranges, which you can fix easily by just going to system assign base addresses. All right, so we have no errors and no warnings. I think we're ready to generate HDL. I'll hit OK. And this will generate. All right, now while that's generating, oh, let's see, that was just the save. Now it's generating. Okay, so now it's generating. If we go back to Quartus, I'm going to open, file open, under the Neos system directory. I'm going to open up this Neos system inst.v, which is a template that shows you how to instantiate this in your wrapper. Notice that it already generated this file, evidently, because I can see the LEDs and the keys are already here. So even though it's still generating files in the background, this must have been one of the first ones it generated. So I'm just going to grab these last 2 lines and copy, go back to lights.v, and then I'm just going to paste them here, and then I'm going to add a comma there. And now I have a little slot that I can use to connect to those 2 new exports. You guys with me? So what I want to export, or what do I want to connect them to? The LEDR is the name of the red LEDs, and those are 17 down to 0. And this part of it is knowing Verilog, and I teach Verilog in my 611 course, but most of you haven't taken that yet. So for this part, this part is something that I'm just giving you that you can copy. So the LED, let's see, those are the LEDRs, and then the LEDGs are, I believe, 8 bits, called LEDG, and then I have an input for the key. I've already got the keys input, so I can see the keys are already there as an input. And then down here, I'm going to use this Verilog convention where you can use curly braces to concatenate two signals. So I'm going to concatenate LEDR will be the most significant 18 bits. LEDG will be the least significant 18 bits. Concatenated together, there will be a 26-bit signal, which will be connected to this 26-bit output, right? And it's 26 bits because I specified that in Platform Designer. And then the keys, I'm going to connect that to key 3 down to 1. So the upper 3 bits of the key input. Everyone see that? And then save that, and that should make the connection. All right, so the generate has completed, so now I can compile this all. So I'll make sure this is saved, save. Right, okay, and you hit the go button, and it should compile the whole design to a bit stream, hopefully. Okay, now while that's running, now we have to go back and revisit the software, because I changed the platform stuff. I added those peripherals, the Uart and the GPIO pins. The BSP, if you remember from last time, the BSP is like the board support package, but it's really a hardware abstraction layer. It's kind of a very thin, sort of like an operating system. It's going to provide some hooks, some functions I can call to access the hardware, right? So part of that is the software has to understand the I/O addresses of the hardware. You guys with me? And so now I have to regenerate the BSP. Make sense? In case you're wondering, every computer has this issue. Linux has something called a device tree that the Linux kernel uses to access this information, I/O addresses and that kind of stuff. It's part of the boot up process. I don't know where Windows gets it, but it must have a similar database of I/O addresses for its initial boot. Okay, so how do we regenerate the BSP? Let's go to the directory first. Data, Designs, Lights, Software. And then I'll go to the Lights BSP directory. And then I need to look this up. I don't remember what it is. It's Neos-2-BSP generate files. I have to source my. Let's see, your local third-party CAD set of files. Altera.bash. Okay, all right. It's Neos-2-BSP-generate files. Now, by the way, I'm using this command because I've already generated the BSP initially. You guys remember we did that last time. So now I just want to update the BSP, so I use this other script. So this is settings, -- settings equals settings BSP, -- BSP, directory equals dot. Okay. All right, that should do it. Okay. Okay, now there's another command called Neos-2 Neos-Bsp Editor. And this is a GUI that comes up. This is the only GUI component we're going to use for this lab with related to the software. Come on. Okay, here it is. Oh. Somewhere. Where'd it go? There it is. Okay, right here. Okay. So these are your settings. There's certain things that there's a few settings that you want to make in the BSP. There's not too many, but one of them is if you do a print, if you issue a print command in your code, you have to tell the BSP how you want it to interpret that print, because a print could, you could be printing to the LCD panel, or you could be printing to the monitor that you have attached, or in our case, we want to print to the Uart, the console. So for that, you need to set up your standard in as the Jtag Uart. Now, by the way, if you had done this before you added the Jtag, you wouldn't have that option. And if you do this again, if you were to add the LCD interface, then it would add the LCD as a option here as well. But right now, the only option we have is the Jtag Uart. So I'm going to set that up as the standard in, standard out, and standard error. And I don't have a timer yet. I don't have a timestamp. And let's see. Software packages, these are turned off. Drivers, everything's turned on. Linker script, these are the linker sections. We'll revisit this on a future lab. So I'm just going to keep everything else as default, hit the generate button, and then exit. All right. Okay, so we've got our BSP, and now hopefully our compile is done. Appears to be. Yes. Okay, let's program the board, program device. Check here, it says USB Blaster under the hardware setup, and I got the soft file here. One thing that you might want to check if you're having issues is if you do a right click on the soft file, that's the bit stream, and go to properties, it'll give you a date, Monday, February 4th at 4:26. That looks like now, a minute ago, right? That means that I can confirm that this is the up-to-date soft file. Sometimes I've seen a lot of cases where you configure the board and it doesn't seem to incorporate the new features you added to the hardware. It's because the soft file, for whatever reason, didn't get updated. Or sometimes, by the way, I'll point this out too. If some of the groups like to take snapshots, like to back up or to copy their project to a new directory for each lab. Like you'll have a lab 1, a lab 2, a lab 3, and that's reasonable. It's a good idea, right? That way you can always go back to a prior lab if you want to scrap, your design and kind of roll it back. If you do that, sometimes this programmer will get confused and it will point to the wrong soft file. It'll, like if you copy this to a lab 2, it'll still be pointing back to the lab 1 soft file. You guys with me on that? So just be aware of that too. All right, hit start, it'll program. You know it's programming because it kind of just goes dim. Now this time, last time when I programmed this, I didn't have any connection made in the hardware to the LEDs. And remember, I pointed out that the LEDs were kind of floating, so they were like dimly lit. Now, the LEDs, you can tell that this worked because the LEDs are completely out now. They're not, there's no light coming from this thing at all because there's now a connection these LEDs are no longer receiving a floating input. They're receiving a hard 0, meaning that they're out. You guys with me on that? Okay, so if you go back to the BSP, there's a file in here called system.h. So there's a driver directory, a HAL directory, it's hardware abstraction layer, object directory, which is the object code, and there's a few other files here at the top level. System.h is an important one because that one is going to have defines in it for some parameters of your system. For example, check this one out. CPU frequency, 50 million, it's 50 megahertz. So for example, if you're counting cycles in your code, you want to find out how much time has passed, you'll need to know what the frequency of the clock is. Some other things in here that most of which I've never used. Data cache is defined in here. So if your code needs to know how big the data cache is for whatever reason. But if you scroll down, each one of the peripherals that you added will have a little section in here. So there's the Jtag Uart section, and that's the Jtag Uart base address. This was the base address that was defined in the platform designer. This was the thing that we had to change because we had overlapping base addresses when we got that error. There's also keys base and LEDs base. And there's some other things in here, but the most important the constant is the base address, because we're going to need to use that when we want to write code that talks to the hardware. So this is kind of the interesting part of this course, is that through this base address, we're going to write software that talks to hardware. This is going to be the software-hardware part of the material here. This is something that normally you don't get to do because operating systems normally do this on your behalf, but now we actually get to interact directly with the hardware. Okay, so we'll go up a level and we'll go to the lights directory and go into our hello world.c. And I think in the tutorial I just said to just kind of wipe this out, right? Yeah, let's just get rid of this. In fact, I've got some code. Yeah, I'm just going to delete all this. Well, actually, you know what? Before I do that, maybe I should run this version because there's a print in there that wasn't working before because we didn't have the console. Let me keep this one for now. All right, so I'm just going to just build this one. So let me just do a make, and that'll compile everything. All right, so now we have an ELF file. That's this ELF file is the output from the build. So we can check February 4th, 4:33, that's the right time. I just built it. So it looks like the build was successful. I didn't see any errors, but this confirms that it did build an ELF file. So the next step is we want to start up, well, there's a couple options here. We can configure the ELF file onto the CPU using GDB like we did last time, or we could there's a command called Neos-Elf download. First thing I want to do is run Neos to terminal. Is it terminal? I think it's terminal, right? Terminal, yeah, Neos 2 terminal. Uh-oh, there's no Jtag cables. Oh, that's not good. So I guess that means Neos 2 soft elf download. Neos 2 configure elf. Let's try that one. Configure soft. All right. So yeah. So if you go to Neos 2 configure soft, that'll download the bit stream to the FPGA. Now I already did that through the programmer, which was this tool, right? But there's a way you can also do it on the command line, and I'm doing that because I want to test and see if it sees the board. It was called what now? Lights.soft. All right, there it is, right? Programming hardware cable not detected. All right, let me restart these guys. Neos-2, configure soft, SIG drive, Z, data, designs, lights, output files, lights.soft. Programming cable not detected. Interesting. Okay, so let's go through what would you do if you get this. Well, the first thing I'll do is I'll check and make sure that can I program through the tool to the GUI. Nope. Oh, look at that. All right. So I went back to the GUI. What happened was I had programmed the board through the GUI here, but now it doesn't see the hardware anymore. You see that? And I don't know why. It could have just been. So I'm going to go ahead and I'm going to turn it off. Oh, did I have the board off? I had the board off. That's why. Sorry. There it is. Now it's back. All right. Somehow the board got turned off. But I didn't know it was off because after I programmed it, remember I pointed out that it stopped blinking, right? All the lights went off. I pointed that out to you. But then somehow I turned it off and I didn't know it was off because it wasn't going through its blinky blink anymore. So let's go back to the command line. I'll see if I can program it through there. And there we go. There we go. There it goes. So notice, I just want to point this out. Notice I programmed it through, there it goes. I programmed the soft file, the bit stream, through the command line. So some of you guys are going to be more comfortable with using the GUI programmer, and some of you guys may be more comfortable with using the command line, right? But you can do either one now. Now that that's programmed, I should be able to run Neos-2-terminal, right? Okay, so running Neos-2-terminal opens up my terminal, my Uart terminal. Now it's not doing anything right now. It's just waiting for there to be a print on the software. It's waiting for the software to print something. That's why I had two of these windows open here. I had two windows open. I closed them. All right, so I'm going to open my second window, and now I need to run the software. So I can go Neos-2-elf-download, Neos-2-download, sorry. And this will download the ELF file. So I want to point out there's a soft file which I downloaded, which configured the FPGA. It created the CPU, and then there's an ELF download which downloads code to the CPU. You have to do them in that order because you can't download program code until the CPU exists. Okay? So now that the CPU exists, I could type Neos-2-download, which is kind of ambiguous, right? But it's the ELF file. It should be called Neos-2-elf-download, but it's just Neos-2-download. All right, what am I downloading? Z, data, designs, lights, software, lights.elf. And you have to pass a -G to this to tell it to not only download, but to go. And there it goes. All right. Well, that's nice, except didn't print anything. All right. Didn't print anything. So now what should I do? Well, I know I was able to configure the FPGA. I know I was able to download the ELF. But I didn't see anything, so it could be. Oh, it did print. Oh, thank you. Sorry, I guess I didn't wait long enough. Okay. Oh, never mind. What I was about to say is, you have to be, you guys are all going to have to, to be able to troubleshoot this stuff when it doesn't work. So if that hadn't worked, I would have known that everything worked fine, except I didn't get a print. So that might have meant that the Uart wasn't, there was a problem with the Uart hardware. It might have not been I might have screwed up a setting in the platform designer, or I might have screwed up the setting for that in the BSP, right? Or maybe my ELF file wasn't ever requesting a print. So the first thing I would have done, had it not printed, is I would have went into GDB and I would have debugged in GDB to make sure that the program that I thought was running and that it was getting to the line that said to print. You guys with me? If that worked, then I would have went and investigated why the Uart wasn't working, right? Because I would have known that the hardware was good, the FPGA was configured, the ELF file was downloading, and obviously it was getting into the memory because the download does a verify too. So, and then the code was running, I could debug it gets to the print, so it was just a problem with the Uart, so I would have drilled down to the Uart. You guys with me? But because it worked, I wasn't able to go through all that. But anyway, yeah, so it prints the value of pi, the program calculates pi. So that's what it's supposed to print. Okay, so I can now do Uart console. That's pretty cool. So now what? I want to be able to do that stuff with the lights now, right? The PIOs that I added. So to do that, I'm gonna edit my. Let's see. I'm gonna go to that directory first. Sig drive Z data designs lights. That's the project directory. Then software. Then lights again, which is. And then I'm gonna modify my hello world. I'm going to use Vim for that. You guys are all familiar with Vim, right? And by the way, you can use Vim or Atom or Sublime or gedit, whatever text editor you want, whatever you're comfortable with. I'm using Vim for this. All right, so I'm going to just actually, should I keep this stuff? I think I'll get rid of it. Why is visual? Oh, there it is. Okay. So I'm going to delete all this stuff now, and I'm going to put in I'm going to put in the code that I gave you guys in the duplicate, go back, bring up the slides, and scroll down to, there's a slide with some code at the very end. Hit end. Here it is. All right, so here's some code. I'm just going to copy and paste it. It's going to look ugly because it always does when you paste from PowerPoint. Okay. Okay. So the first thing you'll notice here is that there's a while one, infinite while loop. Can you guys see this okay? It's small. There's a can I zoom in? There we go. That's better. Okay, so there's an infinite while loop. Anyone, if you guys have programmed Arduino, you know that Arduino is also a bare metal system. There's no operating system, so usually your program code is in a just an infinite loop that just keeps repeating endlessly. So that's pretty common in bare metal embedded systems. The first thing that happens in the loop is that it issues this really confusing and strange function called IO read Altera Avalon PIO data. This is an intrinsic, meaning that it looks like a function, but it's actually it's something that's a stand-in for a load instruction, a load IO instruction. So it's doing a load from keys base. Keys base was defined in system.h. That's the base address of the keys. That was the thing I pointed out, in that system.h in the BSP. That will capture whatever the current state of the keys are. And it'll assign it to a local variable called keys, which is not declared. Why is that not declared? Because I didn't copy all the code, didn't I? Yeah, I didn't. That's the previous slide. Yep. All right. Let's see. So I got to take this stuff and copy that into, sorry. All right, there we go. Okay. So Altera, like a lot of embedded systems, has these special types. Alt_U32 just means unsigned 32-bit integer. It's the same as saying unsigned int, but the problem is in C, if you say unsigned int, you don't really know how big, you don't really know what an unsigned int is. It's unclear. It might be a 64-bit integer, depending on what CPU you're running it on. So by using this instead, it's just an explicit way to know for sure that I'm allocating a local variable that's an unsigned 32-bit, or declaring unsigned 32-bit. Current value, current state, current direction, keys, blah, blah, blah. Right, so basically those are just integers. So keys is going to get an integer representation of what's on the keys. Now that's obviously kind of wasteful because it's a 32-bit number and the keys are only 3 bits, but that's all right. You know, only the low order 3 bits matter. But the other thing is that the keys are active low, and that's something you would only know if you read the manual for the board, which I have linked on the Dropbox. But that's kind of a obscure thing on the board, is that the keys are active low. So if you push, you get a 0. If you release, you get a 1. So you have to, that's something you have to consider there, because when I read this, when I do this line, I'm going to get, if I'm not pushing any keys, I'm going to get a 7. Because 7 is 111, meaning you're not pushing any of the 3 keys. So you're going to get a numeric value of 7 out of there. If I push the left key, I'm going to get a 110, which is a 6. If I push that's the right key. If I push the right key, I'll get a 110, which is 6. And if I push the left key, I'll get a 011, which is 3. Make sense? Okay, so then I'm going to get the keys, and then if keys is not 7, meaning that something's being pushed, and keys is not the current state, and the current state is going to be either one of 3 things. It's going to be first key, which is 3, second key, which is 5, third key, which is 6. Right? So there's going to be 3 states for the 3 different keys I can push, because each key is going to represent a different operating mode. You guys with me? Okay? So this means if I'm changing the operating mode, then if the keys is 3, meaning I'm pushing the first one, I'm going to print a message. The speed is set to 250 milliseconds, and the second key is 150. The third key is 50. Then I'll set the current state, and then once I get done with that, I've basically checked and I've updated my state potentially, and then I'm going to do my maintenance. My normal maintenance is if the current direction is 0, which is left, then I'm going to take, in the current value is 1 shifted by 25 bits. So what this is doing is checking to see if I've got the current direction and the current value. The direction defines which way the little light is moving, because this is basically, I'm just going to move the LED left and right. And the current value is where it's at. And so if I get to one end, I'm going to switch the direction and go back the other side. And if I'm not at one of the ends, I'm just going to do a shift left or right, depending on which direction I'm going. That makes sense? That's a lot of information, but if you look at the code, it's pretty obvious what it's doing. It's just basically just doing a shift one way or the other. Once it gets done with that, it does an I/O write, and it writes to the Ledsbase the current value. So this allows me to write to update the LEDs. Right? So there's two functions here that interact with the hardware. The first one is I/O read Altera Avalon PIO data, and the other one is I/O write Altera Avalon PIO data. So I'm going to be writing to the LEDs, and I'm reading from the keys. Make sense? And hopefully that the names are the same. I got to double check that. Okay, and then this current state thing is just used to control the sleep. So there's a U sleep at the end of this loop that will cause it to sleep for 1/4 of a second, 250,000 microseconds, if I'm in the slow speed, or if I'm in a slightly faster speed, I'll sleep for 125,000 microseconds or 125 milliseconds, an eighth of a second. Or else if I'm in the fastest mode, I'll be 50 milliseconds. You guys with me? Okay, so when I run this, it'll be a bit more clear what's going on here, I think. All right, so I'm going to save that and basically just make. Now, if I got those names wrong, I'm going to. Oh, I'm sorry, I don't want to make it there. I want to make it on Unix. I'm going to make it on Unix. Okay, so I got an error, unknown type, Alt U32. Also, implicit declaration of this I/O read, so something's wrong with the BSP. And LED is base undeclared. Okay, so the reason I'm getting those is I did not put any include files here. See, I'm including standard IO.h, which is part of the BSP, but I don't have all the other good stuff in there that I need. So if I go back to the slides, I'm sure they're in this. That's in the slides, right? Whoops. It's in the slides, right? Yep, right there. Again, I forgot to add some code, so just paste that in there. Now, by the way, system.h is the one I showed you. It just has all the base addresses in there. Altera Avalon PIO regs has, I think that must have the PIO, the IO read, IO write intrinsics. And then the alt types has the, the alt _ U32. Any questions? Okay. All right. So we'll save that and do another build. And looks like we're good, I think. That work? These were from, yeah, right, there was the make there, and then okay, we're good. You check the ELF file. Just make sure 452, good. All right, so let's program it. Download the ELF file. So, just up arrow. All right, check it out. See the lights going, right? And if I push a button, now keep your eye. Now I still have the terminal open over. Oh, by the way, I don't know if you noticed that. The terminal window was still open, and see how it printed program running Uart? That print was in my code. You might have not noticed that because I just pasted it in there. But here's the thing running. Now if I hit a button, please work. That does. All right. There it goes. All right. So I hit the second button, and it said speed set to 150 milliseconds, and it sped up the light. If I hit the third button, now it speeds it up again, and it says speed set to 50, right? Let me go back to the first button that didn't work. There you go. Yeah, the first button didn't work initially because that was the default. It was already in that mode. Make sense? And if I hit, let's say I go fast, but now I hit the rightmost button, remember that's the reset. That'll reset the thing. And so hopefully that'll work. Yep. So when I hit reset, not only did it slow it down, but I got that program running Uart again because it ran the main function again because I reset the whole thing, so main reran. You guys with me? All right, so this lab is now, I've got a console, I've got GPIO, I can talk to the lights and the keys from the software. So this is the base system that we need to have you set up to kind of get started. That's the tutorial portion. The lab, the objective of the first lab is to extend this a bit by adding support for the 7-segment displays. This is kind of this is like sort of an extension of what we've got, but you want to add PIO outputs for these 7-segment displays. You guys are familiar with 7-segment displays from 211, right? There are there's 8 7-segment displays. Now you might say, well, wait a second, how many PIOs is that? Like, well, you could have one PIO that covers all the segments. Each segment is 1 bit, right? So there's 8 digits here. Each one is 7, so 8 times 7 is 56. So there's 56 bits that we need to be able to control from the software. The problem is that if you go over here to Platform Designer and you add a PIO and it has the width, you type 56 and then it says 56 is out of range, 1 to 32. For whatever reason, they limit you to 32 bits. So what that means is you can either split into 2 groups of 28, or better yet, you can just add 8 PIO outputs, 1 for each digit. It's a simpler way to do it because then you don't have to do as much bit manipulation. You guys with me? Right? Then you would just treat it the same way you did those other LEDs, and you can update the hex display. Let's see, where's my code? You can update the hex display by just using this as a guideline and using this function, IO write. So IO write Altera Avalon PIO data, and then, for example, you would just say hex 0 base here, right? Assuming that the name matched up, right? And then you can write a value. Now you might say, what value do I write in? Well, that depends on what you want to show up on the hex. If all 8 hex digits are separate, each one is going to be 7 bits. So you have to have in mind, what you want to show up, and then you have to convert that to a number that you want to be able to put on that hex display. Now keep in mind that these are active, they're active low. So let's say I want to put a digit like 9 on there. The first segment on the top is bit 0, the least significant bit. And then you go kind of clockwise around. So that's 1, 2, 3, 4, 5, and 6. Those are your bits. So if I want to do a 9, actually some people this is always confusing. It's like some people, when they do 9, they don't put the bottom segment on, and other people do. Okay, let's say we don't do let's say we do a 9 like this, right? So that way, the binary representation of this is going to be turn that one on, off, on, right? Where that's 6 and that's 0, right? But remember that these things are active low, meaning that a 0 bit turns on the segment and a 1 bit turns it off. So you actually have to invert this whole thing like that, right? And what is that? That's 0, 1, 2, 3, 4. So that's 2 to the 4th plus 2 to the 3rd, right, is 16 plus 8 is 24. So if you write the value of 24 for this value, if 24 is the value you're writing and the base address is hex 0, that will put a 9 on hex 0, which is the rightmost hex digit on the board. You guys with me? Make sense? That's assuming that you want to put a digit there. In the lab, the lab says that we want to have the same 3 modes. So we've got 3 modes. We've got slow mode. So this is quarter-second mode. Light moves every quarter-second. This is light moves every 1/8 of a second. This is light moves every 20th of a second, right? 50 milliseconds. So those are the 3 modes. Once we add the hex displays, you're going to want to have the hex displays doing different things in each of the 3 modes. In the first mode, let's see, I have to refresh my memory here. Right. In the first mode, the slow mode, the quarter second mode, you want to put random configurations on the hex displays. Random. So they should just be going, should look like, 80s sci-fi, or just random segments going, right? The eighth of a second mode is going to be this thing where you have one segment flowing clockwise around the outer edge of the displays, the hex displays, as shown here, right? So this guy moves to there, and then it moves down, and then it moves down, and then it moves over, and then kind of just rotates around. And then in the fast mode, it'll be a counter that'll just increment on the hex displays, right? It'll increment every 20th of a second, so it'll increment by 20 every second. You guys with me? So this is basically involves you having to add the PIOs to your platform designer. You have to make sure that you add the exports, and then once you add the exports, you have to also add stuff to the lights.v. You have to modify this a little bit to add your hex displays in there, right? I give you hints on how to, or I give you the code in the lab sheet on how to do that. And then you just have to modify your hello world.c to implement that behavior. And you can use, obviously you can use my code as a template because it's got all the control, all the structure. You just put your code inside that existing structure. And you can put everything in the one file, hello world.c. You don't have to add any additional files unless you want to. Hey, any questions about that? And one of the things you'll notice is that I use a usleep in that code, which puts the code to sleep, just a busy loop, while it's waiting. Right? That's put in there to slow it down so you can actually see the light moving. The problem with that is that it makes the buttons a little unresponsive, because if you push the button down while it's sleeping, it may not see the button push. So you'll notice that when you want to change modes, you have to hold down the button for a little while. It's not real snappy. It won't respond to just a quick push of the button. Is there any way to fix that problem? Yeah, you could connect the interrupt. There's an interrupt pin that comes from the buttons. I don't do that. That's up to you if you want to try it. The other option would be to not have it sleep for the whole amount. You could have it, instead of sleeping for like a quarter of a second, you could have it sleep in 20-second increments or something like that, and then in between you could check the button. So you could fix that problem in the code, but a lot of times groups in this class will get frustrated, like why is this thing so unresponsive, right? That's why. It's a limitation of the software, and that's something you could fix in the software if you wanted to add that feature, but it's not required. A lot of people ask, when you're doing the counter, like say I'm in counter mode and I switch to another mode and I go back to counter mode, does the count have to be what you left off, or does it reset back to 0 every time you go back to counter mode? That's up to you. I don't care. I'll leave that up to you. You can have one count that keeps going, and it stops at that count. If you switch to another mode, that's up to you. You guys, does that make sense? You guys follow that? Any questions? Any other questions about that? Okay. Trying to think here if there's anything else that would be helpful for this. So you've got the debugger you can use to diagnose problems. There was something. There's the terminal that you can use for debugging. If you want to print debug messages out to your terminal, you're welcome to do that. There was something. Oh yes, adding files. If you want to add a file, there is a command. There's a Neos command to add a file to your project, because you have a makefile. I think you can just modify the makefile manually if you want to. Like, in other words, if you want to add another source code file, you would have to go in the makefile, right? Otherwise, it'll get ignored. In Eclipse, it was a little easier because you would just add it in Eclipse. But now, you're going to have to put it in the make-file either by editing the make-file, or there is a command, but I don't have that one in the lecture notes. I need to add that. So I'll send a note out to everyone in case you're interested. By the way, most groups in this class will never add another file. They'll just put everything into one big monolithic C file with everything. That's not, not a great way to do it, but you're never going to have that much code, so it's not a problem. Not like we're not writing a lot of code in this class. We're writing a small amount of code that's very low level, and the point of this is to understand how this low level code interacts with the hardware. We're not doing a big project like you do in 240. I actually had projects that I rejected because it was just too many lines of code, and I don't want this to just be like a 240 style course. So you could put everything into one file. It's up to you. Some of you guys are, like to keep your code a little bit more organized and split into separate files. So if you do that, keep in mind that you have to. I'll send out some instructions on how to do that. I just don't have that ready. Forgot about that. Any other questions about this stuff? Okay, also we will be sending out instructions on how to submit this. We don't have that yet either. We have a script that one of the TAs wrote that you'll run in your project directory when you're ready to submit, and it'll run some checks for you, make sure everything is okay. It does some basic checks, it looks for stuff, and then it'll create a compressed file for you that you can upload to Dropbox. And you might say, well, why do we need that? Why not just tar the whole directory up? You can't, because Quartus generates so much crap every time you compile that your project directory will grow and grow over the course of the semester, and you'll very quickly reach the point that if you were to just zip or tar your directory up, your project directory, it'll be too big to upload to Dropbox. And the reason for that is because Quartus generates a lot of intermediate files, but also it generates a simulation model of your system as well that you could simulate. We haven't figured out how to use that yet, but in theory you could simulate this board and not have to you could simulate your code onto a simulation model of the hardware without having to actually have an FPGA board next to you. It's possible, but we have not gotten that to work yet. We've tried, but it's kind of tricky to get that working. But because of all that stuff that gets generated, we're only interested in the code and the designs that you made, the source code. So our script goes and it finds all that stuff and puts it into this file, and then you'll upload that file to Moodle. But we'll send those instructions out before the end of the week. This is going to be due in a week, okay? Next Monday. And then next Monday I'll introduce the video out portion of the course. So we'll add some more peripherals.